Hey everybody, it's Mr. Carr again. Today we're going to be looking at 2.1 day 2. All right, so before we talked about a little bit more rational functions, we're going to analyze radical functions today and also solve radical equations. Okay, so what do we mean with our radical functions? So our graphs are going to look like this. We have certain behaviors that happen from this. Now, some of this you've already kind of covered in previous units. So when we look at this, I want to clarify a few things. Anytime you take an even root, so this is the square root, the fourth root, the sixth root, whatever it is, you're always going to get behavior that looks like this. You're going to have especially if we don't have any kind of shifting, you're going to have a stopping point right here at the origin and continues on in one direction. Okay, so in this specific case, domain range is going to be 0 to infinity. Okay, and again, because with no shifting, it'll always be that way. X and Y intercepts are both at 0, 0, and it's going to be continuous from 0 to infinity. Okay, there's no symmetry here, and it's always increasing. All right. So when we look at our end behaviors as well, you notice how we don't have two end behaviors because go off to infinity. That's that idea. F of x will equal to infinity because it is going to keep increasing forever. But if I look to negative infinity, it doesn't approach it. So we only have this right side end behavior here, not the left side. But if I make it an odd root, like the third root or the fifth root or whatever, that does create this whole function that goes in both directions forever. So now we have negative infinity to infinity. The reason why we cannot take an even root of a negative number, but we can take an odd root of a negative number. That's totally fine. Okay. So some other things that are still apply, like x and y intercept are at 0. Okay. We now actually have origin symmetry. Okay. So whatever there's the positive version here, there's a negative version on like a negative version that's the that has symmetry with it. In this case, it's always increasing, and we do get end behaviors in both directions now. So again, with an odd root, we have the graph that goes forever, but with an even root, it has a stopping point. Okay, so we're going to go ahead and look at these graphs and go ahead and describe their key characteristics, just like we did before. All right, so first thing we notice is it is a square root. All right, so with a square root, we have a domain restriction. We look at this right here, x to the third, well, I should say 2x to the third, has to be greater than or equal to 0. Okay, if I divide by 2 and then take the cube root of everything, what it really boils down to is that x has to be greater than or equal to 0. That's it. So that's my domain. So I'll say 0 to infinity. Now with the range, this graph, the 5 doesn't do much besides cause a stretch. So my range is still going to be 0 to infinity because we're still going to cross that right here at 0, 0. Okay, so just to get my feel for how the graph looks, let me do f of 1. So that's 5 times 2 times 1 to the third power. 5 times the square root of 2 times 1 to the third power. This will end up being 2 times, you know what? That'll be too big of a number anyway. But if I do 1 cubed is 1 times 2 is 2, and then this comes out to 5 root 2. As a decimal number, the square root of 2 comes out to about 7.07. Okay, so at 1, it's going to be way up here at just past the 7 mark. So you can see this is going to be a big graph right away. If I went on to 2 and put 2 in here, that'd be 2 to the third is 8, times 2 is 16, square root of that is 4, 4 times 5 is 20. So just to give you a feel for what's going on, this is just growing very quickly. Okay, so once we get to 2, we'll go all the way up to 20 is the idea. So I can't quite model that. But we have enough to do everything we need. So my intercept is at the point 0, 0. For my end behavior, we have the limit as x approaches. We're just going to do the infinity here because it's not going to go to a negative infinity. So as x approaches infinity, f of x is equal to infinity here. Okay, continuity. It is continuous on the interval of 0 to infinity. Okay, so it's continuous from here on that way because obviously it doesn't exist that way. And increasing or decreasing, this graph is always increasing. So it's increasing on the interval of 0 to infinity. Okay, So that's all my characteristics with that one. Let's take a look at another one with an odd root. So we want to graph and analyze the f of x equals 1/2 the fifth root of 3x minus 4. So this one does have shifting. So we got to be a little bit careful with where we plot some of our points. Okay. I think the biggest thing that's going to help us is technology. So I'm going to go ahead and go to a graphing calculator, and I'll use Desmos in this case, just so I can get some of those key points to make it a little bit easier. Not that one, this one. Okay. It was 1/2 times it was the fifth root. So, whoops. So it'll be this one right here. It'll be the fifth root of 3x minus 4. Okay. So my first key point I'm going to look at is right there, which is actually at 4/3, comma 0. Across here at 0 and the negative 2/3, it looks like. There should be another one that's going to be about 2/3. Let's see here. Looks like it'll be a little bit tough. So let's do this. Let's pull up the table. At 1, we're at negative 0.5. Okay, that's helpful. Okay. So 1, we're at negative 0.5. That was, let's see here. It was crossing again at 1.3. Okay, so 4/3, I'll put that in. That's crossing at 0. Okay. So let's see here. All right. That's enough to give me a feel for this one. So let's come back. We're crossing at 4/3, 0 right there. At 0, it was at, what was that? Negative 0.6, but at 1, it was at negative 0.5. Okay, so right here. Okay, just enough to get me a feel for how it's going to look. Because again, all I really care about is these characteristics. So for my domain, because it's an odd root, we don't have to do anything with what's inside the radical here. We just know that, and so you saw the graph, it's just negative infinity to infinity. There's also going to be no restrictions on my range. This will also be negative infinity to infinity. For my intercepts, okay, we found this one out at 0. It was about negative 0.66. Okay, that's my y-intercept. And for my x-intercept, it was crossing at 4/3, 0. Again, I'm just getting that from the graph. I guess I could plug in 0 here and plug in 0 here to find this one, but we'll talk more about solving these in the future. Okay, end behavior. We do have left-hand and right-hand end behavior. So as, whoops, the limit as x approaches negative infinity, f of x is equal to negative infinity because it's going to go down forever. And the limit as x approaches infinity, f of x equals infinity. Okay, continuity, it is continuous throughout the entire graph. So it's just negative infinity to infinity as a function increasing or decreasing. So way out here, as I go left to right, it is always increasing. It's always going up. So that means it is increasing from negative infinity to infinity. All right. So that's our basic odd root one. So it has a little bit extra to it, but we can find those x and y intercepts, especially by doing our graph, using our technology to help us find those. Now let's talk about solving. Solving radical equations is all about the same ideas that we've done solving since Algebra 1. We need to undo certain operations. So when I look at this, I like to highlight the fact that if I focus on x, the first thing that happens is it's subtracted by 2. Then it's squared. Then it's cube root. And then it's added by 4. So my solving process means I'm going to undo those. I want to get rid of this one, then get rid of this one, then get rid of this one, and then finally get rid of this one. Okay, so we got 4 steps to take care of here. So I work my way backwards. I'm going to subtract 8 to both sides. So I have 4 is equal to the cube root of x minus 2 squared. Now I can undo this cube root by raising both sides to the third power. I think that's the biggest thing to remember about our radical equations. To undo whatever root it is, we do the opposite exponent. If it's a cube root, we raise it to the third power. Square root, raise the second power. Fifth root, raise it to the fifth power. Okay, so we have 4 to the third power, which gives me, I believe, 64. Just double check that real fast. Yep. 64 equals, this will now be x minus 2 squared. From here, we can now square root both sides. But remember from before, if you take the square root of both sides in my solving equations, you have to take the plus or minus square root there. So I get plus or minus 8 is equal to x minus 2. So now my final step is to add 2 to both sides. When I do this, you notice how I am going to have 2 answers here. I'm going to have x is equal to a positive 2 plus 8 and a positive 2 minus 8. Because I got to consider both the plus and minus 8 there. So I get 10 and negative 6. Here's what's one weird thing about our radical functions. Because of the cube root, especially more so the square root, it is possible that we will have what's called extraneous solutions. We need to double check, can I take these and plug them back into the original equation and it still works out? So let's try that. Okay, we're going to check both of these answers here and see if both of them work, one of them or only one of them works. Honestly, possibly neither of them work. So let's see, 12 is equal to the cube root. We'll do 10 minus 2 squared, and then plus 8. So that'll be the cube root. That'll be 10 minus 2 is 8. 8 squared is 64. So cube root of 64 is 4 plus 8. I get 12 equals 12. Okay, so this one checks out. We're good. And let's do the same thing with negative 6. All right, so 12 is equal to the cube root. It'll be negative 6 minus 2 squared, and then plus 8. So negative 6 minus a 2 is a negative 8. But then I square that, it becomes a positive 64. And then the cube root of 64 is 4 plus 8, and I get 12 equals 12 again. So both of these are good answers. So that's why we want to make sure we check, because it's possible I could have created a scenario where one works and the other one doesn't. Okay, so let's take a look at some more examples before we're done with this. We got, two more examples we'll do. I believe one of them will get the extraneous solutions. So, all right, same thing. If I think about this backwards, x is being multiplied, added, square root, subtracted. So I'm going to reverse that order. I'm going to get rid of the, oh, sorry, got ahead of myself. So I noticed that with this, I got a 2x here. So it's not going to be as easy as the previous one where it's going to be able to simplify down to a single variable. I am going to start with adding 3 because I want to get the radical isolated here. 2x plus 3 is equal to the square root of 28x plus 29. Now, again, normally I would just square both sides here to get rid of the square root. And I am going to do that, but I got to be careful how I do the left side. This is going to be 2x plus 3 multiplied by 2x plus 3, which means I'm going to distribute here. Okay, so on the right side, it'll just simplify to 28x plus 29. On the left side, we're going to have 2x times 2x is 4x squared. And I'll have 6x and 6s is going to give me 12x plus 9. It's 28x plus 29. Okay, so from there, go ahead and do your normal solving. Since it's now a quadratic, I want to bring everything to one side, get it equal to 0. So we can subtract 28x and subtract 29. So 4x squared plus a negative 16x. And then minus 20 is equal to 0. Thankfully, this is an easier thing to factor if we go ahead and divide everything by 4 first. So x squared minus 4x minus 5 is equal to 0. And now I can do some factoring. So I've got x minus 5, x plus 1 equal to 0. Use our zero product property, and I'll end up getting x equals 5, x equals negative 1. As before, we want to make sure that we do have 2 answers that work. So I'm going to go ahead and plug both of those back into the original problem. We need to check our solutions. So I'll do the first one. I've got 2 times 5. Does that equal to the square root of 28 times 5 plus 29 and then minus 3? So 2 times 5 gives me 10. 28 times 5, and then plus 29 after that. They give me 169 minus 3. Square root of 169 is 13 minus 3, so 10 equals 10. We're good here. Okay. My other one, 2 times a negative 1, does that equal to the square root of 28 times a negative 1 plus 29, and then minus 3? So we got negative 2. This will be the square root of 28 times negative 1 is negative 28 plus 29 is 1 minus 3. Does negative 2 equal to 1 minus 3? And it does. So negative 2 equals negative 2. So both of them work again. So we're still fine with having both answers here. Okay. For my final example, we're going to up the difficulty a little bit more because it's going to be more distribution. So right now, if you notice, I've got this radical and this radical. So it's going to throw me off a little bit here. But what I can do is I'm going to go ahead and go right to squaring both sides. Okay. So when I square the left side, that one just eliminates the square root symbol. That's fine. But the right side, I'm actually going to be multiplying this. Minus 12 and 1 plus the square root of 2x minus 12. So here, again, I'm going to distribute. It's going to look weird, but I'm going to take 1 times 1 times this radical times 1, and this radical times that radical. So when I do that, we got 1 times 1 is 1. I'm going to get 2 of the square root 2x minus 12s. And once that's going to come from 1 times this and this times 1, add them together. But then when I take this multiplied by this, we're actually just going to be able to get rid of the radicals from there because it's basically the same as taking that squared. So 2x minus 12 from that spot. So again, I took a little bit of a shortcut here because that is technically the distribution of this and this combined. From here, I got another radical. So same goal as before. I want to get that radical as much as I can by itself. So let's bring everything else over to the other side. We'll just subtract 1, I guess, but then also add 12. And we can also subtract 2x over here. So that's gone, that's gone, that's gone. I got x minus 2x is a negative x, and then plus 12 equals 2 times the square root of 2x minus 12. Okay, from here, be a little bit weird. I've got 2 options. I can either take 2 and divide 2 to both sides here. The one part that I don't like about that one is then I got to deal with a fraction when I do the next step. So I'd rather not do that. Instead, I'm going to go ahead and just square both sides right now. When you do that, though, make sure you're including the 2. So I'm squaring 2 as a part of this process. So this one gets distributed just like we've done before. So negative x times negative x is positive x squared. Negative x times 12, we're going to get a negative 24x, and then a positive 144. This gets squared along with everything else. So I'm going to get 4 from that one. So I'm going to have 2 squared and also this squared. That just gets rid of the square root. So it's 2x minus 12 here. All right, almost there. It's a nice long one. 4 gets distributed, and then I'll have a quadratic again that I'm working with. So x squared minus 24x plus 144 is equal to 8x minus 48. Just like before, we're going to get this equal to 0. So subtract 8x and add 48 over. So x squared minus 32x plus 192 is equal to 0. So I'm going to need a little bit more space. So just bring this up here. Okay. And you don't have to do the factoring. It's just, that's my personal preference is to do that way. So x squared minus 32x plus 182. So when I factor this, it's going to end up being a negative 8 and a negative 24. Okay. So from there, zero product property, I'm going to end up getting x equals 8 and x equals 24. All right. As I've done multiple times now, make sure you check both of these answers. See if any of them work and which ones don't work. So I'll start with 8. I've got 8 plus 1 to 1 plus the square root of 2 times 8 minus 12. That'll be the square root of 9 on the left side. I've got 1 plus the square root. That'll be 16 minus 12 is a 4. Square root of 9 comes out to 3. 1 plus 2 now. So 3 equals 3. We're good here with 8. Let's try 24. So square root of 24 plus 1 is equal to 1 times or 1 plus the square root of 2x minus 12. So square root of 25, 1 plus, oh, I put a 2x in there. Run out of space a little bit, but 2 times 25 minus 12. 25. What am I doing here? 24. So 2 times 24 is giving me 48. Minus 12 gives me 36. Square root of 25 is 5. 1 plus 6. 5 does not equal 7. We have our final extraneous solution. Okay, so this one is extraneous here since it did not work on the original problem. So I actually can just cross that off. I only have one good answer here, and that is x equals 8. All right, that is why we have to go check that, because once in a while that will come up. So always check your solutions in the original problem. Make sure they do work. All right, and that is it for today. So again, 2 things. What do our graphs of our radical functions look like? And then what does it look like when we solve our radical equations? They can be very basic, or they get more complicated like this one does. All right, that's it for today. Take care.